Receiving on the bottom end of the spectrum, you cannot miss this. Here is how to make a prediction for any VLF station on Earth. I'm receiving a pretty stable signal from a distance of almost 6,000 kilometers. It's not like shortwave, which allows long-distance communication only during night and under favorable conditions. By the way, did you know, in the early days of radio, shortwave was given to amateurs because it wasn't considered valuable for commercial purpose. In this era, electromechanical VLF transmitters were built, and one of them is still sending messages on special occasions. It's particularly exciting to receive the historic VLF station SAQ Grimeton with a homemade antenna. And there is a lot of mysterious signals to discover. Although my engineering background is helping me a lot finding the right design, I'm still getting excited as a little kid when I see my antennas actually working. Today we will show you how to find out if you can receive SAQ Grimeton and other VLF stations. Stay tuned, getting a prediction for your own location might be an option for you. In addition to proven equations for distance and angle of incidence, the new version is using a two-stage model, providing more accurate and transparent predictions. In a first step, it's calculating the electric field strength in dB microvolts per meter at any desired location on Earth. In reality, a VLF transmitter typically generates such a field strength profile over distance. It's usually higher at night. However, field strength can drop under 1,000 kilometers as superposition of ground and sky wave is causing fading effects stronger than during daytime. A simplified approximation is applied to predict the field strength during the day. During the night, it's varying within this range. Based on the electromagnetic field strength, the tool determines the received signal level for a specific antenna in a second step. I'm demonstrating this with concrete examples now. My database contains location coordinates, frequencies, and effective radiated power of VLF and LF stations. Entering location coordinates instantly yields field strength predictions for the stations I filtered in the database by country, frequency, or other properties. It's crucial that it exceeds atmospheric noise. The so-called spherics are typically reaching 4 to 20 dB microvolt per meter and hertz in the VLF range. I'm considering 20 dB microvolt per meter for this example. I'm a bit skeptic about the prediction of the Australian station Holt because it's in 17,000 kilometers distance. But we will see. If anybody on the US East Coast received it, please let us know in the comments. At 17 kHz, spherics noise is a bit lower, giving a realistic chance to receive SAQ Grimeton. Next, we're computing the signal strength obtained with a loop antenna. Circumference, number of turns, and ohmic losses of the loop are going in here. If the loop is resonant, the capacitor's equivalent series resistance needs to be specified. In case it's operated indoors, you can take penetration loss into account. While stations in North America and strong ones from Europe are no problem with the non-resonant loop, it's too weak to receive Grimeton. However, in resonance it would produce a sufficient signal. At 17 kHz, the atmospheric noise level is minus 132 dBm, which is why we don't see it in the graph. Strictly speaking, the noise level should be specified separately for each frequency. For simplification, I'm assuming now a maximum noise floor of minus 122 dBm for the entire frequency band. We can expect the resonant loop to receive the weaker European stations in Ohio. Now comes a first verification of predictions. My turnable indoor VLF loop, designed in previous videos, is great for this test. Its circumference is 3.14 meters, corresponding to 1 meter in diameter. And its 5 turns loss resistance is 0.14 ohms. It receives even distant stations, although there is a lot of electromagnetic noise from PCs and switching power supplies in my office. Talking about interference, they might be worth watching. In previous videos on Electronics Unmasked, we are explaining how to avoid interference from power supplies, data and feeder cables. My measurements are recorded in the afternoon and in the evening, each station averaged over 5 minutes. I computed a prediction for each station to compare it with actual received signal levels. Besides numbers, I always find a diagram helpful for getting an overview. There's a good correlation between predicted and actual signal levels. All measurements are within the predicted range. That's not bad, isn't it? It appears to be a useful tool. Also interesting, obviously the fading effect mentioned earlier does occur here. The station Raudorfehn is in less than 1000 kilometers distance, and indeed the evening signal is lower than during the day. My test results encouraged me to compute a prediction for my friend Steve AA7U. He is an experienced VLF listener, and we had a discussion whether it would be possible to receive the historic transmitter in Arizona. Tucson is 8,750 kilometers from Grimeton. Certainly a challenge, since SAQ's effective radiated power is much lower than the one of modern VLF stations. In order to protect the historic station, the SAQ team is limiting transmit power to 80 kilowatts. Considering an antenna efficiency of 10%, this results in 8 kilowatt effective radiated. During daytime, the predicted field is 13. At night it's up to 28 dB microvolts per meter, which is barely above the atmospheric noise level. The best chance is likely during Northern Hemisphere's winter, when SAQ transmits in the morning local time, while the night is covering the entire distance. And certainly you will need good luck that local spherics are low. Hope you got some takeaways from the video. Independent from your setup, You can use the field strength prediction in the blue chart to compare whether signals are stronger than the atmospheric noise. The yellow signal level prediction, which is taking your antenna properties into account, can be a bit tricky. For instance, when using a preamp, the atmospheric noise floor as well as the signal levels on your receiver are raised. In this case, you should interpret a predicted signal relative to the noise instead of its absolute signal level. The computation model is valid from 10 kHz up to the lower long wave band. In case you're interested in predictions, let us know. In exchange for a donation to Electronics Unmasked, you will receive both diagrams and a detailed list for your location. Incidentally, I recently received a report from Steve in Arizona showing the Australian station hold as predicted. It seems very likely that the Ohio prediction is just as valid. Furthermore, I tried to receive hold in my office. After nulling out the 20 kHz interference by the antenna diagram, I indeed received the station as predicted. Provided there is interest from our viewers, we could take a deep dive into noise on VLF in a coming video. Just write us in the comments. Now stay tuned and don't forget to support the channel. See you soon in the coming videos.